If you care about Agent ICI, this matters for one simple reason: training longer Eisen agents is still expensive. And the usual shortcuts often hurt generalization. NVIDIA is pitching PivotRL as a middle path, instead of choosing between cheap supervised fine-tuning on heavy end-to-end reinforcement learning. The framework tries to get some of the upside of both. The claim is specific: higher agent IC accuracy, much less rollout cost, and less out-of-domain damage than standard SFT. That matters now because labs are trying to push models into software work, browser casts, terminal control, and tool use, where long trajectories quickly turn into a compute bill. So the key question is not whether PivotRL sounds clever. It is whether its training trick actually targets the part of the problem that wastes compute, while keeping the model from getting narrow and brittle. The main shift is from full trajectory learning to turn level updates. PivotRL starts with trajectories from an SFT dataset, then pulls out assistant turns at model call boundaries as candidate training points. It profiles them offline with a frozen reference policy and looks for what the paper calls pivots. These are states where local on-policy rollouts show mixed outcomes, not uniform success or uniform failure. That detail matters because if every sampled action gets the same result, the learning signal is weak. So instead of spending compute on every turn in a long trajectory, the framework tries to spend it where the uncertainty is real and the gradient is useful. In plain English, PivotRL is not trying to relive the whole interaction. It is trying to find a few moments where the model's choice actually changes the result. Then train hard on those moments. The framework has two core ideas. First is pivot filtering. NVIDIA filters for turns with non-zero reward variance and a low enough reward mean, which means the turn is both difficult and informative. The paper connects that to GRPO, arguing that higher reward variance gives a stronger natural gradient signal. Second is functional rewards. Many agent actions live in generative spaces, like shell commands or search queries, where more than one answer can be valid. Exact string matching punishes good alternatives just because they do not look like the demo. PivotRL replaces that with domain-specific verifiers that check whether an action is acceptable in function, not identical in wording. That can mean schema checks, similarity measures, or lightweight LLM judging. This is a practical change, not just a theoretical one. It makes the reward fit the real task better, especially when agents can solve the same step in multiple valid ways. The evaluation covers for agent IC domains using Q13, 30B, A3B, Thinking 2507 as the base model SWE-Bench, SWE-Bench verified, terminal bench, and browse comp against SFT on the same data. PivotRL posts a larger average gain over the base model, with reported wins on conversational tool use, terminal tasks, and web browsing. The sharper result is outside the training domain. NVIDIA says as average regression of -9.83 across 8 total benchmarks, while PivotRL stayed roughly flat at +0.21. That is the part to watch, because many post-training methods improve the target task by quietly making the model worse elsewhere. On SWE-Bench verified, NVIDIA also says PivotRL reached accuracy comparable to end-to-end RL with 4 times fewer rollout turns, and about 5.5 times faster wall clock training under the same node count. If those numbers hold, That is a meaningful efficiency story, not just a benchmark bump. The signal is clear. PivotRL attacks a real bottleneck in agents, training too much compute spent on turns that do not teach much. It also uses a more realistic reward setup for generative action spaces, which should matter in production-style agent workflows. The paper's strongest claim is not just better in domain scores. It is that the method keeps unrelated capabilities from sliding, which is exactly where simple fine-tuning often disappoints. But there is still noise to filter out. The source is an article summary, not the full paper discussion. So details about verifier quality, rollout budget sensitivity, and failure cases are still thin here. The benchmarks are promising, but they do not automatically tell us how robust PivotRL is across different base models and tool environments. So the grounded takeaway is this PivotRL looks like a smart training efficiency idea with credible early evidence. But the broader generalization story still needs careful replication.